To close the chapter out, we get to put aside the math and look at some results that are typical of hybrid electric vehicle and electric vehicle type operating scenarios to see which methods appear to work well and which don't appear to work well in each setting. So we're going to look at some usage scenarios. We're going to exercise all the methods that we've seen so far, and we're going to compare the performance. All of the scenarios that we look at do use fading memory, but we omit the prefix FM because it just takes up a lot of space. Unless otherwise stated, though, the fading memory forgetting factor is gamma equals 1.0, which of course is not fading at all. We do two cases in this section with gamma equals 1.0 and then one case with gamma equals 0.99, where we, in that third case, we do want the capacity to adjust for aging over time. We are going to use simulation for reasons we'll talk about a little bit, but we need to then come up with reasonable assumptions for the noises in our system. We are going to assume that the individual SOC estimates can be determined to an accuracy of sigma z of 1%. So one standard deviation is 1%. And that's for every SOC estimate. So when I need two of them to compute a difference, I'm going to have 2 times that inaccuracy. This actually, though, is being pretty generous. A 1% estimation error in real life with real sensors and so forth is pretty difficult to achieve. So sigma point common filtering, working in a pretty ideal situation, achieves only about 1% for cells like lithium manganese oxide that have a nice slope to their voltage curve and can be identified with a pretty simple equivalent circuit model. For cells like lithium iron phosphate, which have a really flat voltage curve, it's hard, the voltage information has very little data in it, very little information regarding what SOC is, so the feedback correction of voltage measurement in sigma point common filtering for LFP cells is quite weak. And so in my experience to date, 3% estimation error, 1 sigma, is pretty good. You have to be a little bit careful. Does your estimator use Q or does it use QNOM? Here we're thinking of QNOM being used in the estimator. Otherwise you've got some kind of weird feedback loop where the sigma point common filter depends on the capacity estimate and the capacity estimate depends on the sigma point common filter. So in order to avoid even thinking about any of that, the sigma point common filter used the QNOM in its estimate. And we've already commented that the filter is not very sensitive to the value of capacity in the model, although it is sensitive to other terms. So as long as Q is not too far away from QNOM, that's going to be an okay assumption. Using something like Coulomb counting, though, for your SOC estimation error is going to be really bad, because basically in the equation we're assuming we've got the yi equals q times xi. The yi is accumulated ampere hours, so that is Coulomb counting on that side. So if I'm also Coulomb counting on this side, they kind of cancel each other out, and I get nothing of value from this. So I can't use Coulomb counting for the SOC estimator. I have to use something else, and sigma point common filter seems to give a pretty good match to this method. Other methods besides sigma point common filtering, like extended common filtering, might give SOC estimation error around 2%, say, and simpler methods would probably give you worse. The really nice advantage of using a common filter type of estimator for SOC is that it gives you not only xi, but it gives you sigma xi, these dynamic error bounds, because it gives you the estimates of state of charge and also the variance or standard deviation of those estimates, so that I can compute sigma xi directly and use that as input into the capacity algorithm, because that's one of the required inputs. So there are some limitations to what we can do with SOC in practice right now. I expect that over time people will come up with better models and that will give better estimates and so forth. So that will give us a smaller sigma xi, but that doesn't change anything that we've studied here. It's just going to give us better capacity estimates using the same method because the sigma xi is an input to the method. For the results we show, I'm going to use computer simulation to compute the results. The computer simulation is going to give me a data set of xi, yi, sigma xi, sigma yi. That data set. And that data set is input into the different capacity estimation methods so that I can compare the results. I'm not going to use a real simulation of a cell and so forth. I'm just going to synthetically make up the x and the y. And so there's some reasons for this. It's difficult to constrain some of the factors in a real-life scenario that I can control in a simulation. So it's hard to control the accuracy of an SOC estimation algorithm with random data, but I can prescribe, predict what that accuracy might be and come up with a data set. The accuracy and precision of raw sensor measurements is going to be difficult to control in real life, but I can use that as a tuning knob in my simulation. In the simulation, I'm not going to have to deal with challenges of bias errors and nonlinear errors and things like that, so I can at least look at the best case kind of scenarios for the capacity estimators to see how they work there before I start adding in some of these real life effects to evaluate those as well. Also, with simulation, I can repeat the experiment, changing maybe one parameter only to see what impact that has, but in real life I can't repeat over again. And also, real cells have capacity that do fade over time, and it's difficult or impossible to know the true value of total capacity with which to compare our result. But in simulation, I can know the truth because I'm simulating the data, and so I can compare with confidence to get a baseline. Anyway, those are some reasons that may make sense to you. We do use synthetic data, synthesized or simulated data, to isolate the performance of the total capacity estimation algorithms from everything else when all other factors in the system are somehow idealized. So I generate xi and yi as if I had actually collected them from a real system, but you'll see that they are just random numbers that we generate that correspond to different scenarios, real-world type of scenarios. For this section, we look at 3 different scenarios that are maybe similar to what you would see in a hybrid electric vehicle application. In the next section, we'll look at 3 different scenarios that are closer to what you would probably see in an electric vehicle application, just to show you that there are actually differences in how the algorithms perform depending on how you're going to use them. So we have a hybrid electric vehicle. It uses the battery pack for power mostly and not so much for energy. So it uses, in most cases, a relatively small state of charge window in the battery, maybe from 40% to 60%. That was the early days of the first generation Prius. Nowadays, especially in plug-in vehicles, that has expanded quite a bit. In pure hybrids, it hasn't expanded all that much, but we might use, the most we would use in a hybrid today would be from 20% to 80%, as far as I have heard anyway. So that opened it up quite a bit. I mean, that's 60% versus 20%, and that actually would help, I think, the capacity estimation algorithms a little bit, as we'll see. But with these assumptions, by the way, there's code in the appendix. If you haven't found that already, there is the code that I use to create these simulations. You can cut and paste from the PDF file, stick it in MATLAB, run it. You should get exactly these results. And in fact, for a homework project, that's the first thing you're going to do, and then you're going to change some of the scenarios a little bit to experiment with how these methods work. So if you want to change this assumption to this assumption, go for it, please. I encourage you to do it and see, does it work better, does it work worse, and why do you think that is? And I think you'll learn a lot from it. That's why I give you code. I think that there's more to be learned from you experimenting with the code than there is from you generating the code the first time yourself. Whenever we update a capacity estimate, the true change in state of charge, in this case, if I go from 40 to 60%, that's plus 20. If I go from 60 to 40, that's minus 20. So the true delta SOC maximum is between minus 0.2 and plus 0.2 for those assumptions. What I do in the simulation is whenever I update the the capacity, I say, well, I'm going to assume that occurred because of one of these things, so I randomly choose my xi for that update to be a uniform number between minus 0.2 and plus 0.2. So I don't simulate the whole drive cycle, I don't simulate anything like that, I just simulate a random number between plus minus 0.2. In the HEV application, we have a battery pack that's never fully charged to some precisely known SOC like 100%, and it's never fully discharged to something like 0%. So I can never calibrate my SOC estimate, and every time the total capacity estimate is updated, the two estimates of SOC that I'm using at the SOC at the beginning of the period and SOC at the end of the period both have estimation errors on them. So I compute my x is equal to z at time t2 minus z at time t1, and the overall sigma x squared is, if I assume these updates are independent from each other, which if some time has elapsed is probably close to true. If it's only 1 second that's elapsed, definitely not true. But over maybe a few minutes, probably close enough to true. I can say sigma x squared is 2 times the SOC estimation, sigma z squared. So if I assume a 1% estimation error on SOC, then my sigma x squared is going to be 2 times 0.01 squared. I compute the measured value of xi to be the true value of xi. So true of xi I computed between plus and minus 0.2, but the measurement has some error on it. So the capacity estimation algorithm gets the noisy value or the measured value. So I add zero mean Gaussian random number to the estimate having variance sigma x squared. That's the data it gets to work with. The true value of yi, how many ampere hours changed, is going to be the true value of xi times the nominal capacity of the cell. The true value of change in xi, change in SOC, which is the true value of xi, multiplied by q nom. That's the truth. And then the noise is assumed to be the sum of quantization noises here. Now, quantization error can be very well modeled as a uniform random variable between minus q over 2 and q over 2, where q is the quantum width of your measurement system. And for a uniform random variable between minus q over 2 and q over 2, the variance turns out to be q squared over 12. You can look that up probably in a textbook or figure it out by integrating the uniform distribution. Now that's for one measurement. Now suppose a hybrid electric vehicle, there's really no easy way to say when should I update capacity. I don't want to update it every second because that's going to violate some independence things here and the noise is really going to dominate. Remember, the sensitivity of voltage to capacity kind of gets better over time. If I accumulate over a period of time the change in SOC and the change in amp hours, I'm going to get a better answer. So that's what we're thinking. I'm going to sum up mi different measurements, and here we'll assume we take the measurements at a 1 Hertz rate, and the sensor has a quantizer resolution of Q. So the total noise, the variance of the sum, is going to be Q squared, this quantum here, width squared, times mi, that's how many measurements there are, divided by 12 because of this, and divided by 3600 squared because I'm converting from seconds to hours. Or amp seconds to amp hours, if you want to think about it that way. That is assuming some kind of uncorrelation between the different noises that we have in our measurement sensor, and for a reasonably random current, that's probably not a bad assumption. Okay, so I have a true Yi, I've got a sigma Yi. I can compute the actual noise from, if I sum up a whole lot of uniforms, central limit theorem says I'm going to, in the limit, get a Gaussian, so I can add measurement noise based on this variance to the true Yi. So I've got true Yi, true Xi, noisy Yi, sigma Xi, sigma Yi. Seems like I'm pretty good to go. To compute them, though, I need a couple more quantities. I need, for example, how long is my measurement interval, and what is my quantum Q. For HEV scenario 1, I'm going to assume that the maximum current that can be drawn out of my pack is a plus minus 30C current. That's fairly high, but it's not unheard of. So let's say that, plus minus 30Q. And let's assume we use a 10-bit analog to digital converter to measure current. That means over the full range, I have 1024 quantum levels, or Q is 1 over 1024 times the maximum range. The maximum range is plus minus 30Q, so I'm missing on this page a Q nom there. The Q is 60 times Q nom divided by 1024. The typo is on this page only. The code is correct. So we have Q. I need M. Mi, I'm going to say, is 300 seconds. It's 5 minutes. That was a choice. You can change the code to see how that choice impacts the estimates of capacity. Obviously, if it's shorter, I get more frequent capacity updates, but I'll let you see what you think is a good number for that. Nominal capacity of the cell, I've chosen 10 amp hours. That's probably a little large for a hybrid electric vehicle, a pure hybrid, but that's what I chose. And again, you can feel free to change and see what you find out. In scenario 1, I did not initialize the recursive estimates before I started. In other words, they were initialized to 0. And I present some results here. And on the left-hand side, we have capacity estimates evolving over time, and on the right-hand side, we have some goodness of fit results. So let's look at the left-hand side first. The true capacity is 10 amp hours. You can see that there's a horizontal dashed line at 10. That's the truth, and that's what we're trying to figure out. The thick lines in the plot, blue, green, red, and cyan, although when I look at it, I can pretty much only see blue and cyan because the blue, green, and red are right on top of each other. The green, red, and cyan are right on top of each other, and the blue is not. So there's 3 things here. Those are the same. In this case. The thin lines, like up here, those are the 3 sigma error bounds for the estimates, at least most of the estimates. If we zoom in on this plot, what we'll find is for these, if you zoom in on it, you get a thick line, and there's also the thin line right around it. So the 3 sigma error bounds are for that estimate are so close to that blue line that you can't distinguish them at this scale. All right, so let's think about what that means. First, the blue line on the bottom is the weighted least squares, ordinary least squares method, and it is showing no sign whatsoever of wanting to converge to the truth. This is what I mean by biased. It doesn't matter how many measurements I take, the fact that there is measurement error on both the accumulated ampere hours and on the SOC estimate means that we're going to have a capacity estimation error that doesn't go away. Furthermore, that might be okay if the error bounds still encompass the true value, but we see that the error bounds for that method are ridiculously small. This method is just super confident that it's right, and it's going around bragging about how good it is when everybody looks at it and says, that's not right. You are overconfident. Now, normally we think of having these small estimation bounds as being good. You would like to have small bounds. That looks fantastic. If I just had bounds and the estimate, I would be tricked into thinking this was working well. Well, this is why the goodness of fit thing that we looked at that uses the chi-squared test is really, really valuable. Because look what happens. This blue line, the weighted least squares line here, when I run this test, it says goodness of fit is so close to 0 I can't even tell it a difference from 0 on this plot. The left-hand side, if I look at it and I didn't know what the truth was, I wouldn't know if this was a good estimate or not. I look at that right-hand side and it says this is not a good estimate. There's something seriously wrong with the method that we're using here. And all of that is done numerically. I don't have to guess. I don't have to know the truth to figure that out. I just need data. The data itself tells me that this is a bad estimate. Looking at the 3 other methods, the weighted totally squared, the totally squared, and the approximate weighted totally squared give identical estimates, and they give identical error bounds in this scenario, and they all converge to the neighborhood of the true capacity after a few algorithm updates in the order of 100. After that, they really settle down and they behave very well. And the truth is always within the error bounds of the estimate. The error bounds are plus minus the end a little bit more. This is 3 sigma error bounds, if I remember. So plus minus 0.1. So 0.1 over 10 is 0.1 over 10. That's 1%, isn't it? Yeah, it's a 1% relative error on the capacity estimate, so that's quite good. And the real story is over here on the right. When we do this goodness of fit extra calculation, it says, well, at first it doesn't know if it's super good. It's settling in. Notice at first we have some seeking as it's getting data and warming up, if you will. But after a little bit, it says, nope, I am really confident that the estimate that I'm giving you with its error bounds, so I know it's not perfect, but I'm confident that the method, that the model works for this data. And that's really great news. So any one of those 3 for this scenario would be fine to use. And I think I've said all that. Okay. Scenario number 2 is almost exactly the same. The only difference is that so the weighted least squares method is exactly the same. The weighted totally squares method is exactly the same, but the other 2 methods here, totally squares and the approximate weighted totally squares, both of those, well, in fact, this one too, have the ability to initialize the C1, C2, C3, C4, C5, C6, whichever, those recursive parameters, to something similar to the nominal capacity. And that's what I do in scenario 2, whereas in scenario 1 we initialize them to 0 instead. And we look at the results, and they're really, really similar. So the weighted least squares, again, if you look around here, there's error bounds around it, and it's ridiculously tight. And we look over here, and it says, nope, weighted least squares is awful. Don't use it, please. Please don't use it. Looking at the other three methods, now we have a difference between the weighted total least squares, which I cannot initialize. It's a batch algorithm. And the other two methods, which I can initialize, and I initialize them not to the complete truth. I don't cheat quite that much. I say 9.9 amp hours when the true total capacity is still 10. And so we can see that the dark green line, which I cannot initialize, is a little bit more random at first, and it has a little bit higher error bounds at first. But the other two methods are a little less random and a little bit lower error bounds. So the TLS and AWTLS, because of that initialization, have slightly better, I would say, estimates of the total capacity based on that startup knowledge, especially in the early points. Eventually they kind of converge to the same area, but it takes a while for them to do that. Goodness of fit for all three of those methods, still very good. Nothing to complain about there. I think I said that. Scenario 3, we explore the ability of the algorithm to track a moving value of total capacity. And so this is identical to scenario 2, so I still do the initialization, except I am changing the true total capacity by 1 milliamp hour per measurement update per 5 minutes. And a fading memory forgetting factor of 0.99 is used. So you can see that it goes from 10 at the beginning of time to around 9 here, I think exactly 9 after 1,000 measurements. Each measurement, what did we say, was 5 minutes. So 5,000 minutes of operation. That's a lot. To change 10% capacity in 5,000 minutes, that capacity is really moving. So if we can track at that rate using this algorithm, we're certainly going to be able to track something that is fading at a more realistically slow rate. We have these results plotted below. And in this case, again, the weighted least squares method, if I zoom in, it has error bounds that are ridiculously tight. However, the truth, by the way, is this dotted slanted line. You can see that slants down to there and from up to there. So that's the truth. Here it looks like the weighted least squares method is not as biased. It's actually maybe doing a better job of tracking the capacity estimate. And that's very interesting. But the error bounds are certainly not reliable. And looking at the goodness of fit, the data shows that the method is not reliable because it's just too confident in what's going on. Looking at the other methods, again, I cannot initialize the weighted total least squares method, so its error bounds are a little bit higher at the beginning, and it's seeking a little bit more at the beginning than the others are. But there's not much difference between these to choose between them. In this particular case, it all works quite well. So any of the total least squares or adaptive weighted total least squares would work equally well in this HEV scenario, and we see this kind of a goodness of fit in the result. So the conclusion from the hybrid electric vehicle viewpoint, because I am updating at a constant measurement interval every time. It's always, 5 or 300 samples, I think. It's always 300 samples. That, in fact, is guaranteeing that the error on xi is proportional to the error on yi, because there's no variability between the number of measurements, and every measurement adds a certain amount of noise on the delta yi, whereas I've got a constant amount of noise on the delta xi. So that means that there's no real advantage to this last method, the approximate weighted total least squared, because the total least squared assumptions are met. So I would say if you have a hybrid electric vehicle type scenario where you're updating your total capacity measurement at exactly the same regular intervals every time, total least squares is probably the way to go. It's the simplest method that works really well. So it has finite memory, I can do fading memory, I can track moving targets, I can track stationary targets, it's got realistic error bounds, and it's got a good goodness of fit. Really, really good. That concludes our hybrid electric vehicle scenarios. Now let's go look at some pure electric vehicle scenarios.